This is the 15th lecture of this course, in which we begin a new topic, that is excess carriers. This topic will be covered in 2 lectures. Let us see what are we going to do in this particular topic. First, we will discuss the methods of generating excess carriers. Then we will discuss the concept of injection level and the concept of Quasi-Fermi level. We will then discuss an important parameter, namely the lifetime. So like the energy gap and mobility, this is an important parameter associated with any semiconductor. We will then discuss the direct and indirect recombination phenomena which govern the lifetime, and finally we will discuss surface recombination. Let us begin by discussing the methods of generating excess carriers. The first method is the method of impact ionization. So let us say we have a semiconductor which is N type, and we apply an electric field to this semiconductor. There is a current I flowing through this. We will assume that the semiconductor is uniform. We have already shown that if you plot the current as a function of voltage, the picture would look something like this. That is, the current will increase linearly for small voltages, but for large voltages it will saturate. This is because the drift velocity saturates. If you increase the voltage further in this saturation region, it is found that beyond a critical voltage which is very high, the current starts rapidly increasing again. Now, since the velocity of carriers has saturated by this in this range of voltages, the increase in current here can only be attributed to change in the carrier concentration or increase in the carrier concentration, because the current depends on the carrier concentration and the velocity. So here the carriers are increasing in number beyond this limit, because between any 2 collisions the carriers are gaining energy from the electric field that we have applied, and this energy that is gained is so large that the carrier, when it collides with a silicon atom, it can break a bond and it can generate excess electron hole pairs. So the energy gained by the carrier between 2 collisions is more than the energy gap. Now this is the situation of impact ionization. So this is due to impact ionization. The fields involved here, okay, are of the order of 100 kilovolt per centimeter. So E is greater than 100 kilovolt per centimeter, whereas the fields involved here are of the order of about 20 kilovolt per centimeter. Okay, so which means if this silicon sample is, let us say, 100 microns in length, so 100 microns is 1/100th of a centimeter, then this voltage would correspond to 20 kilovolt per centimeter, that is 20 into 10 power 3 volts per centimeter into 100 microns, that is 10 power minus 2 centimeter. So this amounts to about 200 volts. So this is about 200 volts, whereas this point is 100 kilovolt per centimeter, so it would be about 1000 volts. So it is beyond such high voltages that you are going to see this kind of excess carrier generation. Now in practice, please note that the power dissipated in the sample for such high voltages and these currents is so high that the sample will melt unless you do the experiment in a way in which this high voltage is applied for a short time, so that the total energy that is generated or dissipated is small, okay, and the particular phenomenon of excess carrier generation due to impact ionization can be observed. So this is one way you can create excess carriers. Please note that excess carriers means carriers over and above the equilibrium value. So if this is an n-type sample and doping is, let us say, 10 power 15 per centimeter cube of phosphorus atoms, then under equilibrium conditions it will have about 10 power 15 per centimeter cube of electrons and about 10 power 5 per centimeter cube of holes, okay, of that order. The exact value of hole concentration of holes is Ni square by 10 power 15. So over and above this we are creating carriers, and those are excess carriers. So generally excess carriers are created in pairs, that is, for every excess electron that is created you have an excess hole. Let us discuss another method of generating excess carriers, that is photo-ionization or photo-generation. Now in this case you have a sample which is very thin, and let us assume that you have applied a small voltage to this so that a current flows. Again, for simplicity or for we will assume that this sample is n-type, and the thickness of the sample is, say, about 3 microns, okay. Now obviously this is an imaginary sample because you cannot handle a 3 micron thin sample of semiconductor. So we will assume that this is a thought experiment. We will not discuss the practical aspects of how you can have a 3 micron thin silicon sample. Now let us also assume that its doping is as low as possible so that its resistivity is high, okay. If light is shown on this sample and the frequency of light is such that the h nu is greater than the energy gap of the sample, okay. So the frequency is greater than Eg by h, that is the condition. If this condition is satisfied, then what we will see is the following. So here I am sketching the current I as a function of the frequency of the light, and we will assume that the intensity is kept constant. So we are varying the frequency and the voltage also is kept constant. Now if you see the current picture would look something like this. This is the point where the frequency is exactly equal to Eg upon h. This is a critical frequency. So this current we can call as the dark current I naught. Because this is the current when no light is when the light which is falling, its frequency is very, very small, so no electron hole pairs are being generated. So it is not really, strictly speaking, dark means that the intensity of the light is 0, but here we are keeping the intensity of the light constant but the frequency is small, so that no electron hole pairs can be really generated. When the frequency exceeds this Eg by h, the energy of the photon which is incident on the sample is more than the energy gap, and so each photon can participate in breaking of a silicon bond and creating an excess electron hole pair. Now if the energy is more than Eg by h, that is if your frequency is more, then the number of electron hole pairs will not increase, okay, but what will happen is that the extra energy over and above the energy gap that the photon has, okay, will be dissipated as heat, something as follows. So you look at the energy band diagram, this is Ec and this is Ev. The energy required for an electron to jump from valence band to conduction band and create an electron hole pairs is Eg. So if Eg is the energy of the photon, the entire energy is used up for creating the electron hole pair. If however the energy of the photon is more than Eg, then the electron is going to jump up to some other energy here, okay, where this is the energy, that is the difference between this energy and this energy is the energy that is given by the photon, and then this electron will relax to this free electron will relax to this particular energy state close to the Ec, okay, and this energy will be dissipated as heat. So please note that if the energy is more than Eg, this is Eg, then the extra energy, that is h nu minus Eg, this energy is dissipated as heat. So you do not get extra electron hole pairs because of the extra energy, okay, it is energy is dissipated as heat. So now therefore you note that if you have some way of removing the heat from the sample so that the sample is kept at uniform temperature, then this is the picture that you will get, that there are a certain number of electron hole pairs, excess electron hole pairs created, which are going to increase the conductivity of the sample, and therefore the current is increasing to this value. Now if your intensity of the sample is less, then your this final current that you are getting will be less, okay. So this is increasing intensity. So please understand the difference between intensity and frequency. Intensity of light means how many photons are falling on this sample per unit time per unit area, that is the intensity. So in other words, it can also be regarded as incident power, okay. Another point to note is that all the photons which are falling on the sample will not create electron hole pairs, because some of the light is going to be reflected, not the entire light is going to be absorbed. Another point to note is that the light which is absorbed within a micron or so of the surface which is being illuminated, okay. So within a couple of microns the intensity of light is going to fall to 0. So that is why only a thin layer near the surface is going to absorb the light and create the excess electron hole pairs. This point should be borne in mind, okay. So this is the method of creating excess electron hole pairs by photogeneration or photo-ionization. Let us look at the third method of generating electron hole pairs. So this is called injection. Consider a p-n junction. And supposing we apply a voltage, a forward bias to this. Now in this case what happens is that the p region will inject extra holes into n region, okay, and the n region will inject extra electrons into the p region. This is because this terminal is positive and this is negative, so this positive terminal attracts electrons, from here, and these electrons which are injected into this region are excess electrons over and above the equilibrium value of electrons in the p region. Similarly, this negative terminal attracts these holes, and p region therefore creates holes in this n region which are over and above the equilibrium value. Of course, the sample as a whole will remain charge neutral, that is because the holes which are being injected from p to n will be neutralized by electrons which are injected from these terminals. Now it is important to note that by neutralization we do not mean that the holes and electrons are annihilated. All that it means is the charge is 0. Okay? So this is a unique situation that can happen in a semiconductor where you have excess electrons and in equal number excess holes, so that together they give rise to 0 charge, but excess electrons and excess holes both are present. Okay? So this is the method that is called injection across a forward bias junction. So this is a forward bias junction. So we will show the injection as something like this. If we slightly make the diagram bigger to show this, so the p region is injecting holes and the n region is injecting electrons in this region, and of course the holes which are injected are recombining with electrons which are injected from this terminal, and these electrons are recombining with holes which are injected here, so that as a whole the sample is charge neutral. So this is the picture. So you see how excess electrons and holes are being created by application of a voltage, or they are being injected from an external contact. Okay? So this is a process of injection, and this is the reason why you get a large current in the forward bias junction. If you sketch the current voltage characteristics of this diode, then in the forward bias you get a large current. Okay? So this is the origin. Now if you reverse the voltage polarity, then there is a small current flowing, and beyond a certain critical voltage what happens is that the current increases rapidly. This increase in current for reverse voltages also signifies generation of excess carriers. Okay? This is in the breakdown region. Now these excess carriers can either be created by impact ionization, a process that we have discussed earlier, where a high field is created in a very narrow region called the depletion region at the junction. The details of the operation of the p-n junction will be discussed later elaborately. Now we are just mentioning the method of excess carrier creation. So for this reverse voltage, a high electric field is created near the junction, which may give rise to excess electron hole pairs because of impact ionization, or it could also be what is called tunneling. So tunneling is another method by which excess carriers can be created. So an example of excess carrier creation by tunneling is in a tunnel diode. So we can probably show it here, band to band tunneling. So here you have a p-n junction where this side is heavily doped and this side also is very heavily doped, and when you forward bias this junction, it turns out that your characteristics look something like this. So this is the curve if there is no tunneling, and this portion of the curve is because of tunneling. So what is happening is that because of tunneling, a current starts increasing very rapidly, but the tunneling phenomenon drops off beyond a certain voltage. So this entire current is because of tunneling. And then the normal process of injection that we have discussed takes over. Okay? So in fact this portion is nothing but this portion here, okay, expanded. So on the reverse direction in such diodes, the current starts increasing rapidly, again because of tunneling. So this is also because of tunneling, excess carrier generation because of tunneling. We will not discuss the details of how this tunneling occurs, but we just want to mention that this is one method of generation of excess carriers. So to summarize, excess carriers can be generated by impact ionization as discussed here, that is under the influence of high electric fields. It can be generated by, the excess carriers can be generated by photo-ionization, okay, that is illumination or with the help of photons. It can be generated by band-to-band tunneling, or it can be generated by injection. Okay, excess carriers can be generated by injection mechanism. Now, having discussed the various methods of generating excess carriers, how do you analyze the devices in the presence of excess carriers? That is the topic that we must consider. So in this context, the first important idea that we discuss is the concept of injection level. Now the word injection is used in the context in semiconductor devices to mean any method of generating excess carriers. Okay? So in our earlier discussion so far, we use the word injection to denote creation of excess carriers within a device, okay, because of contacts which are injecting the excess carriers, right. So injection so far was used to mean injection from outside into a semiconductor device, but hereafter the word injection will be used to denote any method of generating excess carriers. Okay. So the injection level refers to the extent to which the semiconductor is disturbed from equilibrium because of excess carriers. Now here the first point to note is the excess carriers are created in pairs. So this can be understood by equation like this. You write the charge balance equation, we have P plus Nd plus minus N minus Na minus is equal to 0. This is the picture under equilibrium. Let us assume that you have some donor type impurities and some acceptor type impurities. So under equilibrium, this is the charge balance equation. Now if you create excess carriers, then the change delta should also be equal to 0. Okay. So therefore what it means is delta P minus delta N is equal to Na minus minus Nd plus, the change in this. So if we assume that the change in the ionization of the impurities is 0, the impurity ionization state does not change, which is a reasonable assumption, okay, then we have the left hand side can be equated to 0. So this means delta P can be assumed to be equal to delta N. This is the situation in most semiconductors. Now here these impurities may mean deep levels or shallow levels, and although we have shown only two types of impurities, one type of donor and other type of acceptor, in principle there can be several different impurities, okay, and all that this will mean is the change in the ionization of the impurities is negligible. So in such a situation you can very easily see that delta P is equal to delta N. So this is the meaning of excess carriers are generated in pairs. So therefore what we will do is we will assume that the symbol delta represents the excess carriers over and above the equilibrium value, okay, either electrons or holes. Since they are equal in number, we use only a single symbol delta. So in other words, your P concentration P in the presence of excess carriers is equal to P naught, which is the equilibrium concentration, plus delta, and the concentration of electrons is equal to equilibrium concentration of electrons plus delta. Now how do you classify the disturbance from equilibrium because of excess carriers? Supposing we show the concentration delta on a log scale, then it is clear that if delta is less than 1/10 of the majority carrier concentration, so this is majority carrier concentration divided by 10. This is what this particular point represents. So if your delta is less than 1/10 of the majority carrier concentration, it is clear that the concentration of carriers which refer to the majority carriers, let us take n-type semiconductor. So the electron concentration. So for delta less than majority carrier concentration by 10, we have n is equal to n naught plus delta, which is a quantity less than n naught by 10, because n naught is the majority carrier concentration, so which is equal to approximately n naught itself. So for delta less than majority carrier concentration by 10, the majority carrier concentration is not disturbed at all. However, note that the minority carrier concentration is disturbed because minority concentration is very, very small, okay. So for this case, minority carrier concentration will definitely be disturbed. So whenever you have excess carrier creation, minority carrier concentration will definitely be disturbed. Now depending on whether the majority carrier concentration is disturbed or not, okay, we classify the injection level into several parts. So this particular region is called low injection level or simply low level. When the majority carrier concentration is not disturbed, okay, this is an example. On the other hand, if your delta is more than 10 times the majority carrier concentration, 10 into majority carrier concentration, okay, that is this point. If delta is here in this region, then both majority and minority carrier concentrations are disturbed, and what you will find is that the number of electrons, the concentration of electrons and holes will tend to become almost equal, okay. So for delta greater than majority carrier concentration into 10, you have n is equal to n naught plus a quantity greater than 10 times n naught, that is your delta, okay. So here this was your delta, here this is your delta, so which is a quantity approximately equal to delta itself. So n is approximately equal to delta itself, okay, because delta is more than 10 times n naught, so this plus this is this quantity itself. Now P is equal to P naught plus delta, which is also approximately equal to delta itself, because P naught is much less than n naught in an n-type semiconductor, okay. So this plus this would be again this itself. So what is happening is n is approximately equal to P, so we can therefore write here because of excess carrier creation, the excess carriers created are so large that number of electrons and number of holes in any unit volume are almost same. So this particular condition is classified as high injection level or high level. And this region will be the intermediate region. So intermediate injection level region, okay, which is neither high nor low. It turns out that the device analysis is simple either under low level conditions or under high level conditions. In both these extreme cases, simplifications are possible, okay. So when the majority carrier concentration is not disturbed at all, or when the electron and hole concentrations in the device almost become equal. They are the two extremes. So under these conditions, the device can be analyzed in a simple way. That is why these two regions are defined. Now let us consider this particular concept of injection level with a numerical example. So let us assume an n-type semiconductor with doping level of 10 power 15 atoms of phosphorus per centimeter cube. Let us show the conditions of electrons and holes on a log scale. So this is the concentration on a log scale. So under equilibrium, your majority carrier concentration is 10 power 15. So this is 10 power 15 per centimeter cube, and your minority carrier concentration would be Ni square by 10 power 15, so that is somewhere here. So this is about 10 power 5 per centimeter cube, okay. So I am just not considering the multiplication constant, okay, because when you take Ni square by 10 power 15, your Ni square will be 10 power 20 into 2.25. So that 2.25 factor I am just ignoring here for simplicity, just to show this particular scale in a simple manner. So here Ni would be somewhere here, exactly in the middle. On a log scale, Ni is exactly in the middle. So this is of the order of 10 power 10 per centimeter cube. For simplicity, I am ignoring the constant. So this is the picture under equilibrium. 10 power 15, this is N naught. 10 power 5, this is P naught, and this is Ni. Now low level injection, supposing you assume delta is equal to (10^12) per centimeter cube because of, let us say, photo-ionization or any other means. So supposing you have excess electron and hole concentrations of 10^12 per centimeter cube. Now your hole concentration would be 10 power 5 plus this 10 power 12, which will approximately be equal to 10 power 12 itself. So excess carrier concentration is equal to the minority carrier concentration. Now 10 power 12, let us locate 10 power 12 on this. So 1/5 of this. So each of this is a factor of 10. So this 10 power 10, 10 power 11, 10 power 12. So this is your concentration P, which is approximately equal to delta itself for low level conditions. Now what is your majority carrier concentration? Your majority carrier concentration is 10 power 12 plus 10 power 15, which is 10 power 15 itself. So your majority carrier concentration is the same here. This is N. So this is your N. Now let us call this delta 1, because this is one particular condition we are considering. So here this is delta 1, P1, and this is N1. So this is the so called low level condition, okay. So P1 is approximately equal to delta 1 and N1 is approximately equal to N0 itself. So here this is N1 approximately equal to N0, the equilibrium concentration. Let us consider another case, that is the high level. This means you have an excess carrier concentration delta 2, which is, let us say, 10 power 16 per centimeter cube, or let us say 10 power 17. Okay. Now, what are your electron and hole concentrations? So, your hole concentration is 10 power 17 plus 10 power 5, which is 10 power 17 itself. Okay. And the electron concentration is 10 power 17 plus 10 power 15, which is again 10 power 17 itself, because 10 power 15 is much less than 10 power 17. So, what you find is electron and hole concentrations both are almost the same. So, this is 10 power 17 okay, the value is in per centimeter cube. And here you have, this is your N2 approximately equal to P2 is approximately equal to delta 2. Okay, so that is a high level injection. So, a log scale very clearly shows both the hole and electron concentrations for low and high level. So, low level the minority carrier concentration is disturbed, but majority carrier concentration almost same as under equilibrium. High level, both majority and both electron and hole concentrations are almost same, okay, and both are disturbed. Okay. So, that is the concept of high and low injection level. In this course, we will be considering the devices under low injection level, because the analysis in that condition is very simple. So, after this, the concept of injection level, next we need to consider the concept of the quasi-Fermi level. Okay. How do you show the effect on the energy band diagram, okay, of the excess carriers? So, quasi-Fermi levels. Now, recall that we said that the electron concentration in a semiconductor can be written in terms of the following equation. N0 is equal to Nc exponential minus Ec minus Ef by kT, and the whole concentration under equilibrium can be written as Nv exponential minus of Ef minus Ev upon kT. Now, both N0 and P0 are characterized by the same Fermi level. Okay, the same Fermi level Ef comes into both these formulae. You can also write the electron and hole concentrations in terms of the deviation from the intrinsic semiconductor. So, for example, I could write N0 is equal to Ni exponential of Ef minus Ei upon kT, and P0 is equal to Ni exponential of Ei minus Ef upon kT. This is another way of writing the same concentration. Now, here the Fermi level is again the same, that is used in both formulae, and the diagram is as follows: Ec, Ev, that is we are drawing the energy band diagram. This is Ei, and let us assume an n-type semiconductor. So, this is your Ef. So EF will be more than EI. Now, can we use similar equations also under non-equilibrium conditions when excess carriers are present? There is nothing that prevents us from using similar equations, that is to relate the electron concentration to the difference between the conduction band edge and a Fermi level. Okay? So we can always use these equations, similar equations under non-equilibrium conditions. What will happen now is that instead of n naught you will have n which will be more than n naught. So therefore the difference EC minus EF should reduce. If your left hand side increases, right hand side should also increase, and this means the difference should reduce. So the EF will have to therefore change to a new value that is called EF suffix n. This is called the quasi-Fermi level for electrons. So it is that Fermi level which, when you substitute in this formula, which is similar to that under equilibrium, you will get the concentration of the electrons, and similarly we can get the concentration of holes also, as we will see. So n equal to Nc exponential minus Ec minus Efn by kT, or here if you were to substitute here, you will get n naught equal to Ni exponential quasi-Fermi level of electrons minus Ei by kT. Okay? So Fermi level under non-equilibrium conditions is called quasi-Fermi level. Now one important point is to be noted. When you want to express the whole concentration, you will note that since left hand side has increased, whole concentration is more because of the presence of excess carriers, because it is P naught plus delta. Right hand side should also increase, which means that this difference should decrease. Okay? So you have a new Fermi level for holes, which is different from the Fermi level under equilibrium. Now this means that the Fermi level should move closer to the valence band edge to have increased hole concentration. But in the same semiconductor, for increased electron concentration, your Fermi level should move closer to the conduction band to have the higher concentration, because this difference should decrease. Now obviously the same Fermi level cannot move close to the conduction band as well as to the valence band. Now this is what is important to note under non-equilibrium. So the quasi-Fermi levels for electrons and for holes are not the same, they are different. The quasi-Fermi level for electrons moves closer to the conduction band edge as compared to the equilibrium, while quasi-Fermi level for holes moves closer to the valence band edge, okay, as compared to equilibrium. So that is the important difference. So we can substitute similarly EFP here instead of EF, and we will get the whole concentration. So this is the concept of quasi-Fermi level. So determining the concentrations in terms of a new Fermi level. Now what is the advantage of this? The advantage will be seen later in analysis, that many forms of equations, okay, under non-equilibrium conditions for devices get simplified if you use this kind of a representation or formula, okay, to relate the energy band parameters and the concentration. So this point will become clearer in the subsequent lectures when we take up analysis of devices. The quasi-Fermi level also has lot of physical significance, and this point also will be clear later. Now before leaving this concept of quasi-Fermi level, let us see what is the quasi-Fermi level picture under low injection level and under high injection level. So under low injection level, since the concentration of electrons, we will be assuming n-type semiconductor, okay, in this example. So under low injection level, the concept of the concentration of majority carriers, that is electrons, will not change significantly. It remains equal to the equilibrium value. Therefore the quasi-Fermi level for electrons remains equal to the equilibrium Fermi level. So if you take low injection level, your EFn is equal to EF. However, the quasi-Fermi level for holes cannot be the same as under equilibrium, because definitely even if it is low injection level, the minority carrier concentration is always disturbed. That is what we saw. So EFP will be closer to the valence band edge. It depends on how much is your excess carrier concentration. So we will show if your excess carrier concentration is, let us say, 10 power 12, That is what we consider in this example for low level. Okay, then your Fermi level would be definitely below EI, because when you have Fermi level at EI, your concentration is Ni, which in silicon is 10 power 10. So if you want 10 power 12, then it will be below this, something like this. Okay, so this is your quasi-Fermi level for holes. So you see EFP and EFN are different, so Fermi level has split. Okay, and further EFP minus EI will be less than EFN minus EI, because this represents 10 power 12. Okay, this deviation represents 10 power 12, while this deviation from EI represents 10 power 15. Okay, we are assuming an n-type semiconductor doping 10 power 15. So low level delta is equal to 10 power 12. This is the picture. So the Fermi level splits into two quasi-Fermi levels. Okay. Now what about high injection level? Under high injection level, your excess hole concentration will be same as excess electron concentration. So your Fermi level would be, say, 10 power 17 if you take, as we have discussed in this example here, okay, as delta 2. Then the picture can be shown separately to avoid confusion. This is EC, this is EV, this is EI, and let us say this is your EF corresponding to equilibrium. Now your majority carrier concentration has increased to 10 power 17, so you will have a new quasi-Fermi level for electrons. This is EFN, and you will have a new quasi-Fermi level for holes exactly at the same distance below. So this is EFP. So this is for delta is equal to 10 power 17 per centimeter cube, high level. Okay. So EFN minus EI is almost equal to EFP minus EI, or EC minus EFN is equal to EV minus EFP. That is the condition at high level. Okay. So the quasi-Fermi levels are situated symmetrically about EI under high injection level conditions. So with this we have completed the discussion on quasi-Fermi level. Next we must consider the important parameter of lifetime, which describes the transient phenomena related to excess carriers. So let us discuss this concept with the help of this figure of photo-ionization. Okay, generation of excess carriers because of light. We keep the voltage constant and you have a current flowing. Supposing you switch on the light at some instant of time, how long does it take for the excess carriers to increase to their steady state value? And when you switch off the impulse, how long does the sample take to come back to equilibrium conditions? Okay, so we can show it on graph. So we will plot the current I as a function of time. We will assume that it is the intensity that we are changing suddenly. Okay, the intensity of light is being changed suddenly, right? So I am going to plot the intensity here. So let us assume the intensity is 0 to start with, and at some instant it is suddenly increased. So light is switched on. It is maintained on for some time and then it is suddenly switched off. So here you have on and here you have off, and these are the instants. Now how do we sketch I as a function of t, the observed current? We will find that you will have a small current called the dark current, I naught. Okay. So this is the dark current, and at this instant the current will start rising, we will find, and will slowly reach the steady state value. Okay, something like charging of a capacitor, something similar to that. And then after it has reached a steady state, let us assume that the light is kept on until the steady state is reached. A sufficiently long duration, it is on. Now at this instant when it is switched off, we find that the current will come back to its dark current value slowly after a decay. Okay, so this is what we will find. In other words, your change in current will not be instantaneous. Okay, the current will not reach a new steady state value instantaneously when the intensity has increased. So there is a delay. Okay, so there is a time which elapses before the sample can respond. Okay, so excess carriers are not generated instantaneously. Okay, so the excess carriers are generated and their concentration starts increasing and then reaches a steady state after some time. Now it is this time that is of interest in the switching performance of devices. Okay, so we will show that these delays associated with the on transient and off transient are related to an important parameter called the lifetime. Let us discuss this situation further. What is the reason for these transient durations? So what is happening here is that moment we have switched on the light, the generation rate has changed suddenly, but the recombination rate has not changed at this instant. So since the generation rate is more than recombination rate, the carriers are being generated. Okay, excess carriers are being generated and the carrier concentration is rising. So excess carrier concentration is, as the excess carrier concentration rises, the recombination rate also goes on rising, because recombination rate depends on the hole and electron concentrations. So here we can say in this region your G is equal to G naught plus G dash, which is excess generation rate, but R, which is equal to R naught plus R dash, this R is less than G because R dash is less than G dash. So R dash is less than G dash in this region. Now I want to emphasize this fact that we are assuming that this particular sample is uniformly, it is absorbing the light in a uniform manner, and so that excess carrier concentration throughout the sample is uniform. So generation rate is also assumed to be uniform. Okay, so this is a thought experiment, it may not be actually true, but in this experiment we are assuming uniform conditions, so that any of these transients that you see here are simply because of the differences between the generation and recombination rates and not because of any carrier movement. Okay, since the carrier concentration is uniform, carriers do not move from one region to another. Now in this portion, what has happened is your G is equal to G naught, because your G dash has become 0, because the light has been switched off and therefore generation rate has dropped to 0. Now recombination rate, however, cannot drop to 0 immediately, so this is R naught plus R dash. Okay, but as the excess carrier concentration starts falling, R dash also starts falling. So in this region, in the steady state beyond this, so here you have R dash equal to 0, G dash is anyway 0 here, so that is equilibrium condition. In this region you have R dash more than G dash. So since recombination rate is more than the generation rate, you have a decay in excess carrier population, whereas here the generation rate is more than the recombination rate, so you have a rise. So in this region, in the steady state portion, you have G dash equal to R dash, so no change in carrier concentration is seen because the recombination rate has risen and become equal to the excess generation rate. However, this is not equilibrium because G dash and R dash both are non-zero, okay, both G dash and R dash are non-zero, whereas here R dash is 0 and G dash is 0, that is why this is equilibrium state. So that is a condition. So the rate of increase of carrier concentration in this region here, we can write d delta by dt, the rate of increase of excess carrier concentration is related to G dash minus R dash. The difference G dash minus R dash is causing this. On the other hand, in this region you have d delta by dt is equal to minus R dash, because the G dash has become 0 and there is an excess recombination, that is why the carrier concentration is falling. So here carrier concentration is rising, okay. So that is the situation from which we need to develop the concept of lifetime. This we will do in the next class.